All right, so in order to prove a contrapositive statement, what we need to do is swap the hypothesis, so our P, and our conclusion Q with each other, and negate both of them. So let's have a look at this example. If n squared is odd, then n is odd for all integer values of n. All right, so it's telling us that we need to prove that if n squared is odd, then n is odd for all integer values of z. So that means our if P then Q statement says that n squared is odd implies that n is odd for all integer values of z. And we can use contrapositive. So that then says our opposite statement of n squared is odd is n squared is even. Our opposite statement of n is odd is n is even, and we need to swap them around, okay? So if n is even, then n squared is even for all integer values of n. So our contrapositive implication looks like this. N is even implies that n squared is even for all integer values of n. All right, so let's have a look. We're going to let n be an integer and n is even. So we know that if n is even, it must be a multiple of 2. So then what we're going to need to do is say, well, let's let n equal 2k, where k is an integer. Okay, and let's square both sides. So I'm going to have that n squared is going to be 2k squared, so that n squared is going to be 4k squared, and I can take out a 2 there, so it becomes 2 times 2k squared. And remember that when we multiply, add or subtract by an integer, we get another integer. So that means that 2k squared must be an integer. And I can then let 2k squared be equal to some other value of m, which is also an integer. So therefore, n squared is 2 times m, which is even. Because anything that's a multiple 2 is even. So the way contrapositive works, that if you can show that your contrapositive statement is true, then our original statement is true. So therefore, if the contrapositive is true, the original statement must be true, and so therefore n squared being odd implies that n is odd.